So by definition, derivatives y is equal to fx. So if you take a derivative of y function with respect to x, or maybe we can say just fx or dx, then simplicity we can just say y prime or y dot, or if you just want to use fx you can prime or fx prime. So by definition this is limit delta x goes and x plus delta x minus fx. So this one just shows that how much of y or f function change over delta x when delta x goes to almost 0. So the rate of change of fx. Let's say you are running or walking and moving to your first position to a certain position, okay? So time is equal to 0, you start from here, and then time is equal to t1, you are here, and time is equal to t2, you are here. So if you make the position y, let's say this is y coordinate, so y is function of time and this is time, so you start from 0 here, and then t1 you just slowly walk, so you arrived here, and t2 you kind of a little bit more faster, so you just arrived y2, let's say this is y1 displacement. So if you make all those kind of connections, then probably you will have those kind of graphs, position versus time graphs. Then I want to get the average velocity during the time from t1 to t2. Okay, so the average velocity is displacement, which is y2 minus y1 over delta t. So I want to say between t1 t2 is delta t. So if you look at this average velocity, this is a slope of this linear line. Okay, so this line passing these 2 points. So if you just look at time t2 time t1, so this is delta t and this is displacement delta y. So the slope of these graphs shows the average velocity. Then if you try to make delta t is very, very small, which means t1, t2 is getting close to each other, then that's the limitation, right? That's the limit. So if you make delta t is the 0, y2, y1 or delta t, that's the definition of derivatives. So y prime, okay? So this is becomes instantaneous velocity at a given time, right? Because t1, t2 is getting close, then the slope of a given time becomes the instantaneous velocity. This slide shows basic derivatives rule. Then you know that the constant derivatives is 0, and power rule, the power, if you take the function with the power, then the power term comes in front of it, and then you just subtract 1 to become a new power of the function. And this is sum rule, and you can take each derivatives and add later. And then product rule, if two function is multiplied, then you take a derivatives of second one plus and take first derivatives of your first term. And this is quotient rule. If two function is kind of one function is divided by the second function, then this one is a little bit unique. So the function on the bottom is squared, and everything is divided by that term. And then I want to spend more time about the chain rule, okay? Because many of students are still confused about how they use the chain rule. And chain rule is very simple actually to use it. So for example, I want there's a function of y, and this is function of ft. So if you take a derivative of y with respect to time, it's simple. You can just take derivatives of ft, and which is f prime, because this y function, y is a function of t, so you can directly take derivative of y with respect to time. But so however, let's say your y is the function of, for example, a u, okay? So let's say this is 2x, I'm sorry, this is 2u squared and u plus 1. Then if you take derivatives y with respect to time t, then u is not constant, but u is not t. So you cannot take derivatives directly this y function with respect to time, because the y is a function of u, not the function of t. But let's say the u is another function of t, okay? Then you can use you can take derivatives of y with respect to time t, because we know that this parameter u is another function of time t. So in this one, we just a little bit manipulate it, and du like that. So you have to take derivatives of y with respect to u first, because your y is defined by the u parameter, and after that u can be differentiated with respect to time t. So this is called the chain rule, okay? Because this one is the same. This is kind of making a bridge between the dy and dt. So in this one, we can easily take a derivatives the first function, and then you can take derivatives the second one using this one. This is chain rule. So for example, function of sine, okay, and this is sine x squared. I want to take derivatives of dy and dx. Right now, we learned that sine x can be differentiated like a cosine x, but this is sine x squared. It's not the same. So in this one, you can say, let's say u is x squared, then your function can be changed like a u, and then u is x squared. Then what you need to do is dy dt is equal to dy over du and du over dt. So dy over du is cosine u, and du over dx is 2x, right? So this one is cosine x squared and 2x. So this is the result of your differentiations using chain rule. And then let me talk about trigonometry function. So we have 6 trigonometry functions here. sine and cosine and tangent, and then reciprocal of sine is cosecant, and reciprocal of cosine is second, and the reciprocal of tangent is cotangent. So we have 6 trigonometric function. Then this is right angle triangle that has a right angle on the right side. Okay, this is 90 degree. Then this sine theta is determined by b over c. So sometimes it's confusing between sine theta and cosine theta. What's the ratio? Is it c over b or b over c? So for example, cosine theta, so cosine is, this is c, so that's why you start from here to go there. So that's why c is on the bottom and then a is over there. So a over c is cosine. How about the sine? The sine, you can write down the s is like that. So this is your s. So you start from here, this is your last. So your c goes to the bottom, and then your opposite goes to the top. So b over c. Okay. How about tangent? Tangent is t. So this is tangent. So you start from here, goes to there. So your starting point is on the bottom a, and then goes to your opposite b. So b over a is tangent theta. That's the way to memorize it, so you won't forget, or you won't be confused about what's the ratio. You won't be confused between sine theta and cosine theta. Then how about the derivatives of trigonometric function? So sine, if you take derivatives of sine, which is cosine, cosine is negative sine, and so on. So you have to memorize it, or let me just quickly show you one thing to memorize this. The way I memorize this one is that you can locate sine x on here, okay? And then I want to locate my cosine x on here, and then I want to locate my tangent x here, okay? Then I want to locate my reciprocal of sine the opposite way. So this is the opposite direction locations. So this one should be cosecant, and the reciprocal of cosine is second x, and reciprocal of tangent is cotangent, okay, x, like that. So you just located the 6 trigonometric function like that. And then if you take derivatives of x, it just goes to this way, so it becomes cosine. If you take derivatives cosine, it goes back to the sine. But if you have a c in front of the function name, then you just put the negative. And then in this one, if you take derivatives of tangent, it's just going down. But when you go down, you have to multiply 2 times of this one. So tangent, so that's why if you take derivatives of tangent, it becomes second x squared, okay? And then if you take derivatives of second x, it goes up. But if instead of multiplying the tangent x 2 times, it becomes the second x times tangent x, like that. How about this one? If you take derivatives of cotangent, it going down becomes cosecant, but see, this one has a c, so you take a negative, and since this one is going down, it becomes the square of cosecant. So that's why if you take derivatives of cotangent, it becomes negative and square. And if you take a derivatives of cosecant, it's going up, but you first it becomes its own times cotangent x. So that's why you have to use this one. But this one has a c, that's why you have to take a negative as well. This is the way I kind of memorize these derivatives of trigonometric function. And lastly, I want to say that you can take a derivative of a vector as well. Okay. So let's say this is a vector. Okay. So this is a vector, but a vector is keep changing as a function of, let's say, scalar u. It can be t or x, anything, but in here, let's say this is u. Maybe you can say t. Okay, so as a function of time, a vector is keep changing its magnitude and direction as well. So for example, a certain time later, your a vector becomes this one. Okay. So let's say t1 a vector is here, but a t2 a vector becomes like that. It just moves like that. So this is a vector. So a vector is a function of time. Okay, but the vector functions, you can take derivatives of a vector over the t as well. Okay. So you can still use exactly same equations. Delta t goes to 0, and then a vector t plus delta t minus a vector t, and then delta t is going to 0. But if you look at these two vectors, so right now this is the original vector when time is equal to t1, and certain time later the a vector change its direction and magnitude like that. But if you look at these equations, you have to subtract your first vector from your second vector. So if you subtract it, it becomes this vector, right? This vector. So let's say this is delta a vector. So then this one becomes dt like that. So this is the answer of your differentiations, but the direction, okay, direction is different from the direction of your original one. So your original vector is this direction, but delta A is this directions. So that's why you can still use same equations of differentiations, but you have to understand that your direction will change once you take derivatives of your vector. Then we can find the differentiation of vector is distributives. So like here, the vector a plus b can be defined by the derivatives of each vector plus and add these two. And this is scalar, this is vector. Then this is scalar function, this is vector functions. Then we can still use the product rule. So first scalar differentiations times vector plus scalar function times the vector derivatives, and this is a product, so we use the product rule. And this is a cross product, this is a dot product, so we can still use the product rule, but you use the dot here, you use the dot. And if this is a cross product, you use the cross product between these two. And then lastly, I told you that the vector A can be broken into different components, right? So a vector is, let's say, axi, and ayj, and azk, something like that. So if you do the a vector derivatives, then you can say ax over dti, okay, and plus ax di over dt, because I just use this equations, this rule. So when I take care of the first term, I have to take derivatives my scalar first and then the vector, okay? And plus dy over dt j and ay dj over dt and something like that. But in here, what is di over dj over dt? So ij is a unit vector. This is a unit vector for xy coordinates. So even over the time, this unit vector does not change. That's why this one should be 0. The rate of change should be 0. That's why simply the result of the derivatives of vector A using components looks like AX derivatives and Y component derivatives J and Z component derivatives and K, simply. So that's why in this slide, if you want to take this A vector in the space, take a derivatives with respect to time, it can be written like that, and then the rate of change of unit vector is 0.